There's no place to hide as I step inside the classroom. Dr. Doom, prepare for the boom. Bam, oh man, I slam jam. Now I scream like Tarzan, woo. I'm rigging, disrupting, my style is awesome. I'm causing more family feuds than Richard Dawson.
All right, we're going to talk about mechanical advantages. We're going to go over counting tensions and estimating system efficiencies. So this is be part one, which will just be going over counting tensions within your system. So I'm going to work off a couple of screens here. So this is going to be a quick talk about just counting tensions and mechanical advantage system. For some, this technique is used when first learning mechanical advantage systems to figure out what they're even building. And second, kind of checking other people's systems so they got a view on what's going on. There's a lot of confusion sometimes on moving pulleys versus stationary pulleys and what adds to the mechanical advantage. This is just an easy way to go through that. Others use it for determining the mechanical advantage, more complicated systems like Spanish Burtons, which we have in here also, and certain complex systems that are used in mountaineering and rigging and climbing. The other side of it is a lot of people will use this just to estimate what the forces are on the anchor. You're going to see that depending on how we have it rigged, whether we're pulling against the anchor or we're pulling with the anchor, we'll change the force that is placed on that anchor when we're actually pulling. And in some cases, when we're pulling, it'll actually be more force on our anchor than what it is on our load. So that's typically the framework in which counting tensions comes in handy. We'll go into a little bit more examples of the relevance of it and where it's irrelevant. This is very Newtonian in nature, meaning that it's linear physics, and nothing in the real world where you work is linear. It's all nonlinear. So there's a lot of other things that are going to play a role in what your true actual mechanical advantage is, but this is actually where we have to start. So getting into this, we will start right here. So this is just going to be a quick review of linear physics and what MAs do. In Newtonian physics, it's linear by nature. It's very straightforward. It's additive, not multiplicative. And you can actually reduce it, meaning that you can use reductionism to reduce every single little part of it, add it together, and get the accurate whole of what it is, also called superposition. So with that, that is indicative of something that's linear, which we can do here. Once we start going into the nonlinear realm, where we're looking at different frictions, not only within the pulleys or within your system, but friction over edges, bending rigidity of your ropes, the nonlinear phenomena that occurs in manufacturing of your ropes anyways, then a lot of those principles go out the window and we can't use those as often. So real quick on here, if the rope knot, and we're talking about continuous mechanical advantages here. So if the knot of your rope starts at the load, which is the case right here on the far left on the 1-to-1, also the case on your 3-to-1 and 5-to-1 over here, then your mechanical advantage is going to be odd. If the knot starts at your anchor, which is the case right here on your 2-to-1, then you know that your mechanical advantage is going to be even. Like we said before, that's in building these systems up. Once you start getting into systems that are piggybacked and other systems, you got to watch it a little bit closer. So starting off with that, just very, very basic. If I would start pulling on this rope just from here without having even this pulley, as I pull up, for every foot that I pull up, that load will raise. When I go through a change of direction, which is just a fixed pulley, so this pulley is not moving at all, it's attached to my anchor, and in this case I'm pulling down, that is going to be a 1-to-1. And we'll kind of get over counting tensions here in a second, but it will require 1 foot of pull for me to lift up 1 foot from the load. When we get into, let's say, this 2-to-1, how the energy is dispersed here is I'm pulling here from this haul line. The other end of my rope is attached to an anchor. That rope then goes down to my load. There's a pulley, and now I'm pulling up on that. In that case, I've got to pull 2 feet to be able to move the load 1 foot. So in the end, if you think about levers, that longer the lever it is, the easier it is to lift up, but every little part, I've got to pull down a lot more to get any kind of lift from that other end. And it's very similar in that. We can actually look at it if you want to get nerded out on it. We can actually look at fixed pulleys are very similar in nature to if we go across the board into, let's say, some of your lifting techniques in technical rescue, that would be equivalent to your class 1 lever, where a moving pulley in this case would be equivalent to your class 2 lever. And if you think about it from a lever standpoint, if you think about when you're building a class 1 lever, right, I'm going to put my effort here. So if my load is sitting here, I'm going to put effort down here so that effort goes in. So I have my effort, I've got a fulcrum, and then I've got my load that I'm lifting. And so if you think about it that way, I've got my effort here from the haul line. I've got my fulcrum right here on my pulley, which is a fixed anchor pulley, and then here I have my load. So it's actually the exact same mechanics as when we're talking about class 1 levers. If I'm looking at my class 2 lever, which is typically used to roll something over, in that case, I have my effort here, which has to be pushed up. On that, I then have my load, which is kind of in the middle, and then this lever that I have is usually going underneath that, and then it's articulating with the ground, and that's my fulcrum. So I actually have the effort, load, and then fulcrum as I'm doing a class 2 lever. That's really what we have here too. So we have our effort load, or our effort right here. Then here we have our load, and then I have the fulcrum there. So it matches the same sequential process that your levers do also. That was kind of a side note. If we get into a 3-to-1, and we'll talk about why this is a 3-to-1 and this is a 5-to-1 complex, but on a 3-to-1, I then have to lift 3 feet, pull 3 feet of rope to be able to move that load 1 foot. So although I have 1/3 of the weight in my hands as I'm pulling, the anchor has the other 2/3 of the weight, making it easier for me to pull. Then getting into a complex system here, this is your 5-to-1, in which I have now got to pull 5 feet of rope to be able to move my load 1 foot. So in that, just like a lever, much easier to lift, although I've got to do a lot more movement with it, is what makes it easier. So we'll get into counting tensions of why this is even a 5-to-1, that's a 3-to-1, 2-to-1, obviously, and a 1-to-1. But just understand that this is linear, and when we're talking about it, we are not talking about friction or anything else in there, and we'll kind of give you some of the background into that. So this assumes that whoever's listening to this has a basic understanding of mechanical advantage rope systems. What is presented in this video cast is straight up linear physics, so it's Newtonian in nature, not representative of the real world application, but this is where we need to start. So when we get into building in efficiencies, we're going to start it off the same way, except we're going to start adding in things like friction to be able to understand what our true mechanical advantage actually is. We'll be counting tensions within a mechanical advantage system to determine the theoretical mechanical advantage. I've got some asterisks going in here. There's a bunch of different definitions. So if you go ahead and look in any kind of Google or Bing searches, you're going to see a bunch of varied definitions for what ideal mechanical advantage, theoretical mechanical advantage, and actual mechanical advantage is. Actually, the actual mechanical advantage is pretty straightforward. That is, in the end, how much you're pulling, how much force you have to pull, with everything accounted for from edge, as far as what kind of edge you're dealing with, what the coefficient of friction is on that, what the friction is within your pulleys, all those things is what makes up your actual mechanical advantage when all is said and done. Where the confusion comes in is when you're talking about ideal MAs and theoretical MAs. So for our purposes on this one, we're going to go with more of a classical understanding of theoretical MAs from the physics world, which says basically a theoretical MA is that theoretical type of thing in science where this is what it is before we add anything else into it. So theoretical MA for our purposes assumes a frictionless world. So there is no friction in your pulleys. There's no frictions over the edge. It's kind of that make-believe world, that theoretical world. The ideal MA, a lot of times when you read and look into some of the encyclopedias and some of the physics books compared to some of the rope rescue books, and you are going to see different people use it in different ways. So be cautious of that. Ideal for us is if I've got a bag of whatever, I can make, if I've got pulleys with bushings in them that aren't as efficient, and I've got a couple that are very efficient pulleys like Rock Exotica with closed seal bearing pulleys in them. My ideal is what would be ideal for me to be able to make or construct, in what order do I put the pulleys to create the most efficient pulley system in there. Some of your definitions out there will say ideal and theoretical are the same thing, blah, blah, blah. For us, just putting that into the background, theoretical for us is there is no friction in your system. It's kind of make-believe, and then we'll get into dealing with efficiencies and understanding how that coordinates into our system and what kind of impact that has. All right, concepts to remember. There are sometimes easy ways to find the MA of a simple or compound haul system. We can look at just counting the line supporting, and we'll talk about that when we look at some examples, supporting the load as a simple system, or we can actually see where one MA is pulling on another MA, know that that's a compound, see what the MA is pulling on the other MA, and then we can actually multiply those together to get what that is. So we don't always have to use the techniques that we're teaching you here as far as counting tensions, although they work on everything. There's shortcuts around that you may want to use. When we do need to be able to count tensions is typically when we start dealing with complex systems, or your complex systems also include Spanish burden systems or variants that you'll see in there, usually within mountaineering or sometimes within rescue. So that is really the only way we can tell what the mechanical advantage is. There's 3 ways of kind of finding out what your MA is. If you're just building some random crap around the firehouse or on the floor of your team room. And out of all 3, counting tensions is probably the most applicable way that you can do in the field very quickly and be able to give a thumbs up or thumbs down to what you believe that system is and how much force is on your anchor. So, just as a comparison, we're going to be counting tensions within our system, being able to follow that through the entire line, starting where our haul system is, or our haul line is. The other ways you could do it is I could take that load and I could weigh it and get an exact representation of what that load weighs, and then build my mechanical advantage system or whatever I think it is, and then put that same measuring device to show how many newtons of force I'm pulling, and knowing what the end weight is, and then pulling on that one, then I can divide that out and say that's what I have. Most of us don't roll around with very elaborate systems to detect what the measurement devices are on that. Not probably the way to go. The other one to do is I can put that load up, and from where my load is, I can draw exactly where 1 foot is and mark that. And then as soon as I do the same thing on my haul line, is start right where I start with my haul line, pull my haul line, and when my load reaches that foot, then I count how much rope I pulled, and then that will give you the mechanical advantage. Also not really applicable. So counting tensions is kind of the way in which we're gonna hit on this. So we always start counting tensions from the haul line, where the rescuer's hands grab to pull the rope, and work our way back through the system all the way to our load. We'll always start with 1 tension when we input on the haul line. The reason that we do that is regardless of how much you can pull, we just count that as 1 tension. So if you get up on that rope and you pull 100 pounds, still 1 tension, because it's going to be that force that you're putting into it is the 1 on the mechanical advantage ratio. So that is your input. So if I'm inputting 20 pounds of force, or I'm inputting 200 pounds of force, it's still going to be whatever force I input is 1 unit. So that is the 1. The first number in your mechanical advantage, the 3, the 5, the 6, that is what's going to be outputted. So that is the magnification of your 1 input. So if I input 100 pounds, I get 300 pounds out. If I input 100 pounds, I get 500 pounds out. So that is how that ratio goes. So we are going to always start with 1 tension, because it's irregardless of how much force we're actually putting into that gets magnified. All prusiks in our system, so when we talk prusiks, we're talking rope grabs, are always going to be an addition sign. So it's the T block, it's the rope man 2. It's that is always going to be an addition sign, except for if you happen to be using a camming device as a progressive capture, then that all that does is hold your load when you let go of the rope. So whether that's a prusik or that's an internal camming device, or a gree or whatever the hell you're using, that is not going to be a point of addition. So it's just going to be those things that are used as rope grabs. And we stop at all rope grabs to see if we need to perform addition. Lastly, before we get started, is pulleys are a force multiplier. So pulleys, regardless of whether they're moving or they're fixed on an anchor or they're moving up in your mechanical advantage, don't know that they're moving or they're fixed. They just multiply force. So if we go back to simple machines and we look at a pulley, pulleys are used to magnify force. So they'll magnify that force, whether it's at an anchor or whether it's as a rope grab that's moving. In the end, obviously, only moving pulleys are articulating with your mechanical advantage or adding to your mechanical advantage, where a fixed pulley is just that. It's just a change of direction. So people get that kind of confused, that only moving pulleys add to a multiplication of their force. And that's not true. We're going to see that on anchors, and that's something you got to be kind of cognizant about. So if we look at the regular pulley, this kind of gives you the cheat for counting tensions in there. So what we see on this Rock Exotica micro pulley is how strong this pulley is. It's 30 kilonewtons strong, and that shows you that if you have 15 kilonewtons on one side, you have to have 15 kilonewtons on the other. And that can be expressed in tensions, right? And that's what we're expressing it in. So if you think about it, if one tension comes into this pulley, one tension has to come out, which means that pulley is now supporting two tensions. So if you think about it, equal and opposite reaction. So if I'm pulling down on this side's raising up, and I'm pulling down with 100 pounds of force, and this is, 100 pounds. So this is raising up. I have 100 pounds of force here. I have 100 pounds of force here, both being put onto that pulley. So 200 pounds is what's being seen at the apex of that pulley. So whatever's going in on one side is equal on the other side when we're counting tensions like this. So one comes in, one has to come out. So just remember, look at any pulley that you have, and that's usually how their weight is depicted on there. The MA is the final number that's sitting at the load when we're counting tensions, and don't ignore the anchor number. A lot of people just kind of roll right past the anchor number, not realizing that when we're pulling against that anchor, we're having a magnified force. If we're pulling with the anchor, that's what I'm going to be wanting to use if I've got an anchor that's maybe somewhat questionable, or I definitely don't want to overload that. And we'll kind of see what that force looks like. All right, so counting tensions. A lot of folks will use counting tensions just for complex MAs. We teach it starting from the get-go. So as soon as we even start talking about a 1-to-1 or a 2-to-1, we're already adding how to count tensions into it, just because most people are very familiar with a 1-to-1, a 2-to-1, a 3-to-1. And so when we're looking at that, we want to start them understanding the concept of counting tensions on systems that they're already familiar with. It just makes it easier. So when we get into those complex systems, they have more of a foundational toolbox to understand what exactly is going on. So just like we said before, we're going to start at the end of the haul line with an initial input of 1. The MA is the number that terminates at the load, and the anchor number is also important. So we have that depicted in all of our examples also. So on this 1-to-1, my force is going to be pulling down. This is where I grab, boom, to pull that load up, right? So we already know from our previous example that I pull 1 foot, load raises 1 foot on that 1-to-1. So as I pull down, I have a 1. That 1 that I'm pulling on is transferred up to this pulley. So as I'm pulling down, my 1 unit of tension, regardless if it's 100 pounds, 50 pounds, 200 pounds, is going up this thing. So if I have 1 that comes in, 1 has to come out. Equal and opposite, just like what we saw in that previous slide right up here. So if 1 comes in, 1 has to come out. So when we're looking at it in this form, 1 comes in, 1 comes out, which means I have 2 tensions up here. That 1 continues. So 1 comes in, 1 comes out, 1 goes all the way down to my load, and I'm left with 1. We know our mechanical advantage is whatever that number is after we finish going through our whole system that terminates at the load. So all we have here is a 1-to-1 mechanical advantage. When we look at this example, right, I start pulling on my haul line, so I'm going to be pulling up to lift this load up. So as that 1 tension goes down, 1 tension goes down. If 1 goes in, 1 comes out of that pulley, and 2 is left at the apex. Obviously, it's upside down. So 2 is left there. That 1 comes all the way back up and terminates at my anchor. So I only have 1 load, 1 tension at my anchor, but I have 2 at my load, which means I have a 2-to-1 mechanical advantage. If we go back to the first example here, and let's just put numbers to it so we see the reason that this anchor number is 2, which is bigger than what my MA number is here, which is my load, which is 1, is because I'm pulling against my anchor. So your pulleys multiply force. So when I look at that, I pull down with 1 tension. 1 tension is on the other side because it's being raised up at the same amount of force that I'm putting into it for linear stuff. And that means 2 is over here. So let's just let's say that this is 100 pounds down here, 100-pound load. So I'm inputting 100 pounds to raise that. Actually, because of friction, it would be a little bit more, but whatever. So I'm inputting 1. So I've got 100 pounds coming in, I have 100 pounds over here, which means I have 200 pounds being supported by my pulley. So when I'm pulling against that anchor, although I'm only lifting 100 pounds, as I'm pulling and magnification is occurring, then I do have 200 pounds of force being placed on my anchor at that point. All right, moving over here, this is where people kind of get mixed up a little bit, is just by adding a change of direction. So if you think about lifting up a casualty in an elevator shaft, so I could be doing a 2-to-1 where my anchor is up by me because that's where the rope knot's starting. And if it starts at my anchor, the rope, and leaves from there, I know that's going to be even. So I know I've got an even MA on this one. And it goes down to my casualty. There's a pulley on my casualty, and I am lifting up. It's going to be difficult to sit there and squat going up. So I may want to put a change of direction in. So that's what we did here. So this is just a 2-to-1 with a change of direction. This pulley is actually on my anchor. So it's a fixed pulley staying right here at my anchor. So as I pull down on this, this is all part of my anchor. So in it, it doesn't add or change my mechanical advantage when I'm counting tensions. It will change my efficiency, but that's another PowerPoint. So as I'm pulling down on this, if one comes in, one comes out, and I've got 2 on this anchor point. That one continues down, one goes in, one comes out, I've got 2 on my load, one comes up and terminates. So when I add these together, I've got 2 tensions over here, 1 tension over here. So my anchor is seeing 3 tensions, and my load is 2, which is a 2-to-1 with a change of direction. So change of directions do not alter your mechanical advantage. It just adds in a change of direction. So my fixed pulleys do not add to my mechanical advantage, only my moving pulleys do. And we'll kind of see, when you see how to count efficiencies, you'll see how that impacts your system dynamics and behavior a little bit more. So let's move on to other systems here. Now we get into using things that have a rope grab. So these are depicted just as prussics. These can be T-block, they can be a rope man, whatever you need. These up here is just your progressive capture. So this is your anchor point with your progressive capture. In this case, we illustrated that with just a prussic on there for simplicity's sake. So on this system, we're looking at it and we say, okay, you know what? The rope is starting from my load and going up, so I know it's going to be odd. As we look at this, I can look at my haul line. So as I'm pulling up, I'm inputting 1 tension. 1 tension goes into this pulley. 1 tension has to come out of that pulley. And that means that I have 2 tensions sitting right here on my prussic line at the apex of that pulley, because I have 1 over here, 1 over there. I've got to have 2 over here. So as 1 comes in, 1 comes out, I have 2 sitting on that prussic. And as my 1 goes up into my progressive capture, 1 has to come out. So I have 2 sitting on my anchor point. As that 1 comes out, it goes down all the way to the prussic. And every time I see a prussic, like what we said, you should picture an addition sign. So you can kind of see what we've done in there and just add kind of a plus sign. So because that prussic or that rope grab will always be holding a certain amount of tension from this pulley here. So in this case, it's holding 2 tensions. So as 1 comes down, 1 meets with my prussic. So 1 plus 2 is 3. So from this point down, I have 3 tensions. So that is a 3-to-1 Z drag. So that's very, very common mechanical advantage that we use. And that is the case. So over here, to kind of work us through what happens when we do a change of direction and what that means as far as force goes, all we did was do a 3-to-1 Z drag, but we added a change of direction. So it for one way or another, if we're doing an elevator shaft, it just makes it easier for us to pull down than to continually pull up. So we added a change of direction in there. And what we wanted to show you on this is that it didn't change the mechanical advantage. It's just a mechanical advantage with a change of direction. So I input 1 tension. 1 tension comes in, 1 tension comes out. I have 2 at the apex. As that 1 tension moves down to another pulley, 1 tension comes in, 1 tension has to come out. So now I have 2 sitting on that prussic, which will be a plus sign. As that 1 tension moves up to my progressive capture, 1 goes in, 1 comes out. 2 is at my anchor. That 1 continues down, meets up with the prussic. The prussic's holding 2. 1 plus 2 is 3. I've got a 3-to-1 Z drag with a change of direction. Meanwhile, I have 4 tensions on my anchor. So why is that important? Just for simplicity, I'm a product of Southern Education, so we'll keep it super easy. Let's say I'm lifting a load that's approximately 300 pounds. So just knowing that we can input, my haulers can input about 100 pounds of force, we feel comfortable going with a 3-to-1, right? We always want to go with the least amount of MA that we can reasonably handle, just because it's more efficient, meaning that I don't have to pull as much rope. Although I could go to a 5-to-1 to make it easier. Do we need it? If we don't need it, let's not do it. So that way we're not finding ourselves pulling 5 feet of rope to move it only 1 foot. In this case, we're moving 3 feet of rope to move it 1 foot. But I've got 4 on my anchor. Why? Because I'm pulling against my anchor. That is what's adding the magnification of force. So with that, if I'm raising something that's 300 pounds, let's work that through. So if I'm raising something 300 pounds and I input 100 pounds of force, because it's on a 3-to-1, I know I'll have to input approximately 100 pounds of force. 100 goes in, 100 goes out. 200 pounds of force is sitting on this anchor. 100 pounds comes down, 100 pounds goes in, 100 pounds goes out. 200 pounds of force is sitting on that prusik. 100 pounds of force goes up through my progressive capture. 100 pounds of force comes out. 200 pounds are sitting up here. 100 pounds goes and meets my prusik plus 200. So I've got 300 pounds of force, which is equivalent to what my 3-to-1 is. So that all adds up nicely. But as I'm pulling, meaning only when I'm pulling do pulleys magnify their force, I will have approximately 400 pounds of force on my anchor in this scenario. When I let go and my progressive capture holds it, then it's only going to be this line that's holding my 300 pounds of force. Only when I'm pulling, actually, and rope is moving through your pulleys, your carabiners, whatever devices you're using, that's the only time where you have the magnification of force. All right, so moving over here, we're going to get into some kooky ones. So as we said before, if I looked at these and I wanted to do just a very simplistic way of counting tensions, a lot of people say, hey, just count the amount of lines that are supporting your load, which is fine for simple mechanical advantages. And you can actually, if you can break your mechanical advantages up, you can do that for compounds also. So if I looked at this and I just drew a box right around this area here, I said, all right, how many ropes are, when I'm pulling, how many ropes are supporting my load? I can make 1, 2, 3, it's 3-to-1, right? And that's completely accurate. The problem is once we get into complex systems and most of the Spanish Burtons, we no longer can just count how many ropes they're supporting, right? If I would do the same thing over here, I would draw a box around and still know these aren't doing anything supporting it, right? These aren't supporting in an upward manner my load. I still just have 1, 2, 3. That's just a change of direction. So that's not supporting my rope at all. That's a pull down line. That goes out the door when we start dealing with complexes. So here is a basic Spanish Burton 3-to-1. So when you look at this, this is done a lot of times in mountaineering because you can turn around and use this for modified systems where I have just enough rope to reach my load, and maybe I have some cordelette, some 6-mo cordelette, or I can even do it with maybe a Dyneema sling or anything like that to start creating that mechanical advantage. So this is a little bit more of an improv way of doing it. So this is a separate rope right here, just this small little bit right here, and my main line is the main piece going from my load around through my progressive capture. So to figure this out, I start where my hands go to pull. So I'm always going to be with 1. So if 1 goes in, 1 comes out, and 2 is sitting on that prusik, which is actually going to be pulling my main line. So 1 goes in, 1 comes out, 2 is sitting there, 1 comes down and terminates on my prusik. So this prusik is only seeing 1 tension. So this is nothing more than a sling put in a carabiner, then wrapped up through a pulley, and I'm pulling down. Or it could be a knotted cordelette, so it'd be like a figure 8, a double bite bowline, whatever on that carabiner right here. And then that small piece of cordelette that I'm using is going up through that pulley and back down. So right there, 1 goes in, 1 comes out, 1 terminates here. So I only have 1 on my prusik down here, but I do have 2 up here, right? Because it's at the apex of my pulley. So now as I'm pulling down, what is that doing up here to my main line? It's pulling down with 2 tensions. So if 2 goes in, 2 comes out, and I have 4 on this anchor. As this moves down, my 2, right, 2 goes in, 2 goes out, 2 comes down, meets with my 1. We add those together to get 3. So 3-to-1 Spanish bowline. All right, moving in. Getting to a little bit more common on the first 2 here. So this is nothing more than a 5-to-1 simple mechanical advantage. What we did is usually that's seen with a double pulley here. We use the ARS in a different version of a roll clip to make it kind of easy for us instead of dedicating ourselves to a double pulley. But a lot of times you'll see simple 5-to-1s done with a double pulley. So what we did for the purpose of counting these is we just separated the double pulley into 2 singles so you can kind of see what's going on the front and back end of your double pulley. So right off the bat, these are my anchor points right here. This is my moving pulley, which would be a double pulley. We just separate those out. One comes in, one comes out. Two is sitting on the back side of that sheave. One goes in, one comes out. Two is at the apex on this anchor. One continues down into the second part of my double pulley, into the front there, and I have one come in, one come out. So I have another two. So that one double pulley has 4 tensions, force put into them. So 4 is sitting on that prusik. Continuing up, one goes into my progressive capture, one comes out. I have additional 2 on this anchor point. That one comes down, meets with the 4 that was come up from the double pulley, right? So if you think about 1, 2, 3, 4, 4 tensions right there. 4 plus 1 is 5, and I've got a 5-to-1 simple mechanical advantage, right? So my simple mechanical advantage, I understand is simple because I've got one continuous rope moving through my system. All my pulleys are moving in one direction, but more importantly, which separates it from a compound, is all my pulleys are moving at the same speed. That's how I know I don't have a mechanical advantage on top of a mechanical advantage, because both of those would be pulling at 2 different speeds. So your pulleys would be moving at 2 different rates in your system. So that is a simple mechanical advantage. When we get over here to the other side, now we basically have to what looks to be like what the 3-to-1 with the change of direction was, except we don't have the anchor point. We actually put it on with a prusik onto the back side of my progressive capture. So this is my load side. This is my haul side. So prusik gets put onto that side of my MA. So in doing this, this is not me talking about simple systems, right? My pulleys right now are not going to be moving at the same rate because I have a MA pulling on an MA, but also they're not moving in the same direction. They're going to be compressing against each other. They're going to be collapsing towards each other. So when we look at it, a compound mechanical advantage, which I think we'll see in the next one, is a simple MA pulling on a simple MA where all the pulleys are moving in the same direction, although they will be moving at different rates. So I can break that. A 3-to-1, pulling on a 3-to-1 is going to be a 9-to-1. So when I can break up 2 simple systems, which we'll show in a 9-to-1, I can take those 2 and I multiply them together, and that's my mechanical advantage. On a complex, we can't. So think about your Spanish Burtons over here. Think about your complexes like this. So when I look at this, this is how we do it. I'm pulling on this line, so I have 1 come in, 1 come out. 2 is sitting here on this prusik. 1 comes down, 1 comes out. I have 2 sitting on this prusik because it's the apex of the pulley. Now my 1 coming up here, 1 meets with this 2 that's been sitting on this prusik. So 1 plus 2 is 3. So now in this portion here, I have 3 tensions. So if 3 goes in, 3 has to come out, which gives me 6 on my anchor. That 3 moves down this rope all the way until it hits this prusik, which is holding 2 tensions. So 3 plus 2 is 5, and that's a 5-to-1 complex system. When we move over here, and I'll kind of enlarge this just a little bit when we're talking about it, this is used as a crevasse. It's kind of a variant of a Spanish Burton. This red line that you see in here is, just like before in the 3-to-1 Spanish Burton, is another piece of rope, cordelet, or webbing. So on this, it's actually locked off here on the anchor. So this can be a cordelet tied in a figure 8 into a double bite bowline, or it could be a sling of Dyneema, a long Dyneema sling that's just put through the carabiner and then routed through my pulley down here. So when you get into this, this looks an awful lot like a 3-to-1, except this is not attached straight to the prusik. There's another MA system in there. So when we look at it, we're like, what the hell is it? Let's figure this out. So we'll count tensions on it. So we go in and we go, 1 goes in, 1 comes out. 2 is sitting on this pull line right here, which is what our sling or cordelet or whatever is attached to. Is it's fixed here and it's fixed in there. So as we pull in, 1 goes in, 1 comes out. Now we need to, because this is pulling, as we pull up on this, this is being pulled on a mechanical advantage. So because we have 2 goes in, 2 comes out. 2 terminates up here on the anchor. So because 2 goes in, 2 comes out, at the apex of that, I have 4 sitting on that prusik. So now when we continue this up, on the original, 1 goes in, 1 goes out. 1 goes in, 1 comes out, 2's here. That 1 comes all the way down and meets in on that main line with the 4, and then I have a 4-to-1 crevasse. All right, getting into even goofier stuff here on the Spanish Burton variants here is when we look at this, this is where counting tensions comes in place, man. To look at this and think that you're going to count how many lines they're supporting and this and that and get an accurate count, you won't be. So when we look at this, this is a clove hitch. So let's just think cordelet. So I've got a knot coming onto this. It's going through here. This can be a carabiner, it can be a pulley, whatever that is. It doesn't matter when we're counting tensions. It will matter when we're counting efficiencies. So a knot here, it runs through this carabiner, comes down here and terminates into a clove hitch. Or it could be two knots, doesn't matter. So if we say this is a clove hitch, then that other running into the clove hitch comes out here, and that's what we're pulling on, right? So you can see how that's all going to kind of collapse down. So in the end, one comes in, one's going to come out, and it terminates right here on this carabiner. So one comes in, one comes out. I have two. So two is what's pulling this line through that pulley, through that carabiner. So if two comes in, two comes out, I now have four sitting up at the apex of this carabiner. That two continues down and terminates in the clove hitch. So I have 1 plus 2, so 3 is sitting on that prusik. I have 4 up here. So because as I'm pulling this down, this is pulling through my progressive capture. 4 comes in, 4 comes out. I have 8 up here on my anchor. That 4 comes down, meets with my prusik here that's holding 3 tensions. 4 plus 3 is 7. So it's a 7-to-1 Spanish Burton. Now we'll get into a little bit with, and I'll just raise this up, come over here, into a compound system. So when we're looking at this, this is nothing more. If we break this up, we got a 3-to-1 here. So if this was my haul line stopping right here, I'm pulling, that's a 3-to-1. Then what we ended up doing is building a 3-to-1 on top of a 3-to-1. So no problem whatsoever if you're sitting there going, okay, I'm just going to count what I got holding it. So I have a 3-to-1 being hoisted, being hauled by a 3-to-1. 3 times 3 is 9. You got it. But to double check what we're looking at and to double check what we're looking at as far as anchor strength, we can start right here. 1 goes in, 1 comes out. I've got 2 sitting here. 1 comes in, 1 comes out. That 1 that follows down meets with my 2, so that's 3. 1 plus 2 is 3. So here is 3. So 3 goes in, 3 comes out, which means I have 6 sitting here on this prusik. As 3 comes in, 3 comes in, 3 comes out. I got 6 at my anchor. That 3 that came out travels down until it hits the prusik. When I hit that prusik, 3 plus 6 is 9. It's a 9-to-1 compound. All right, this next slide, we took some different examples that you'll see in marketing from various manufacturing companies, and we took some from physics classes that you'll see on some textbooks, encyclopedias and things like that, and figured we would just go through some of that. So when you're looking at marketing material, talking to vendors or manufacturers, and you see their pictures, you can kind of get a scope on what they're actually talking about. And once we talk about efficiencies, then you'll be able to call BS on some of the stuff that they're actually trying to sell you, which isn't that awesome sometimes. So let's look at this one here. So when we look at this, this is taken out of Petzl's, which is pretty cool. So realize that although you're seeing a carabiner here, we're going to count it just like it's a pulley, right? As far as 1 going in and 1 going out, and managing it the exact same way. So you'll see the differences between carabiners and pulleys in the efficiencies, but for our purposes, 1 tension goes in, 1 tension goes out for this portion. So here we can obviously see where the haul line is. 1 comes in, 1 comes out. I have 2 sitting right here on this carabiner, which is knotted to probably a long prusik cord here, which is tied into a rope grab up here. So 1 comes in, 1 comes out, 1 terminates up here on that blue line. It terminates where the rope grab is. And I have 2 being hauled through this pulley. So if 2 comes in, 2 has to come out. 4 is sitting, in this case, on a T-block. So 4 is sitting there. That 2 that came out continues up. 2 plus 1 is 3. So now I have 3 going into this microtraction. 3 has to come out the microtraction, which means I would have 6 up here on my anchor. So that 3 that came out, which is actually my load line here, that 3 travels down to my T-block. The T-block is holding 4. So 3 plus 4 is 7, and that's a 7-to-1 mechanical advantage. This one I had to kind of throw in because it was kind of interesting. So this is one of the earliest written or drawn depicted versions of a Spanish Burton, which are wildly efficient. And you'll see that in the efficiency podcast or the video cast. what's interesting about this was actually the basic drawing that came out of Leonardo da Vinci's notebooks. So that was one of the earliest graphical representations of Spanish burns was from Leonardo da Vinci. What's interesting about this is we can follow this through. So this is obviously our hull line here. So obviously one comes in, one comes out. I've got 2 on this anchor point. One is continuing down, one comes in, one comes out, and then it terminates. So this is actually terminated with just 1. I've got 2 over here, 1 over here. We won't worry about the anchor too much on this one, just figure out the MA. So 1 comes in, 1 comes out, 1 comes in, 1 comes out, and I've got a 2. That 2 tensions is pulling on another system. So this, you can see, is a whole nother system, like a backwards type of J. So that 2 to 1, or 2 tensions goes in. So 2 goes in, 2 comes out, I've got 4. So as 4 goes in, 4 comes out, I've got 8 in my next system. 8 goes in, 8 comes out, I got 16. 16 goes in, 16 comes out, and I've got 32. So when we look at that system, that is a bunch of different rope segments, right? But it maintains a really high efficiency. So is something applicable for what we're doing? Probably not. But in the end, it's good practice for counting your tensions. And when you get into efficiencies, it actually plays a huge role in understanding how you can maximize the efficiency of any of your systems. So that is a Spanish Burton. So basically, we're looking at a 32 to 1 mechanical advantage in that system. That is Spanish Burton in origin. Over here, we'll take a look at this one. This goes by a bunch of different names. You'll see different names from, from obviously it's a 2 to 1 pulling on a 2 to 1 to change direction, but it can be flying J's because of the J look that it has on there. This is obviously even because the end of my rope starts at my anchor. So if we just follow that down and we go in and figure out where our system goes, we start from our hull line with 1. 1 tension goes in, 1 tension comes out. 2 is up here at the anchor. 1 tension comes in, 1 tension comes out and terminates. Now, because 1 tension went in, 1 tension came out, I have 2 sitting right here on the apex of this pulley, which is being pulled by the other part of our 2 to 1. So now because this is pulling on this, it goes 2 goes in, 2 goes out, 1 comes in, 1 comes out, I've got 2. So now 2 goes in, 2 goes out down here, which is giving me my 4 to 1. So this is a 4 to 1 compound mechanical advantage. Compound because I have 2 simple systems, a 2 to 1 and a 2 to 1 with the change of direction, and the 2 to 1's pulling on the other 2 to 1. So once again, 1 comes in, 1 comes out, 1 comes in, 1 comes out, 2 is sitting here. So now that 2 is sitting here, 2 comes in, 2 comes out, 4 is down here. Whatever number I'm left with at my load is my mechanical advantage. And here I think we have another Petzl example, which is a good one too. So we can look at this real quick and be like, hey, I recognize this as a 3 to 1. The hull line of my 3 to 1 is being pulled by a 2 to 1. So in a case like that, I can go, okay, I know that this is going to be a 6 to 1 mechanical advantage because 2 times 3 is 6. But let's just double check this, counting tensions, and we'll also be able to see what we have on our anchor. And so as we look at that, this is obviously my hull line, which is enacting everything. So if 1 comes in, 1 comes out, and it terminates, and I have 2 sitting on this prusik. Right now, because I have 2 sitting here, 2 is going into this. So if 2 goes in, 2 comes out, which means I have 4. When 2 goes in, 2 comes out, which means I have 4 up here on my anchor. That 2 comes down, meets with what I had previously, which is 4. And 2 plus 4 is 6, and I've got my 6 to 1. So that's just another way to back up what you're counting already, even if you use the cut portion where you can figure this out. I know that that's a 6 to 1 mechanical advantage. All right, moving on. We're going to do a whole separate podcast of different ways that you can rig your piggyback systems. In your piggyback system, super easy is you have a main line that's on a progressive capture. It's basically just a 1 to 1. We attach a secondary or a separate mechanical advantage that usually that's pre-rigged, like the examples over here, onto our main line, and we pull. So in the end, whatever the mechanical advantage is that we're attaching onto our main line is what the MA is going to be. So our main line must have a progressive capture device in order to be able to reset this piggyback system. But our progressive capture on our main line does not always have to be really uber efficient. So we could just use a one-way munter if we wanted to. Any system at all, because all we're doing is as we pull off our piggyback system, our main line gets slack in it. And because all of our weight is on our piggyback system, we can't reset that forward once it collapses all the way. So at that point, we take all that slack out of our main line to be able to capture our load. Then we release the capture on our piggyback system, and that's what allows us to reset it because our main line is being held by its own progressive capture. So under normal conditions, until we get into some voodoo stuff, that does not have to be efficient whatsoever. So as you see here, all we did was attach a 3-to-1 onto our main line, and it is nothing more than a 3-to-1 piggyback system. When we look at some of the ones commercially available, this is the new one from North American Rescue that's hitting on the website really soon, which is their individual mechanical advantage system, which is a pocket mechanical advantage system that articulates with almost everything. So on this, if we would place this on here, I'm going to just enlarge this a little bit. We can see that this is set up into a set of 4, set of 5 type of example. So in this place, if this rope grab goes onto our main line, I've got 1, 2, 3, 4 sections supporting that. So this is the 4-to-1 configuration. I could flip this around backwards and it would be a 5-to-1, which we kind of showed here with the Aztec system, which is also just a small little personal haul system that you can attach onto any rope system. So in this configuration, we can notice we see 1, 2, 3, 4 lines supporting it. This line over here is our haul line, which is being pulled downward, so only 4 lines supporting it. That's the 4-to-1 configuration, but we could flip it back upside down, attach this onto our rope, and then we have 1, 2, 3, 4, 5, and this would be our 5-to-1 configuration where we're pulling upwards on this way. So your set of 4s can be reversed, and you need to get a 4-to-1 or 5-to-1, but there's a lot more voodoo that you can do with that. In the end, whatever MA you're putting onto your main line is going to be what your mechanical advantage is. So for our purpose of this, last one I want to hit, and then we'll round up this part 1, is if you look at a lot of our systems, let me just go backwards here to show an example. This will probably be good. If you look at this 5-to-1 complex system, when I'm pulling, I've got more weight on my anchor than I do hauling. So although I have 5 tensions down here, I have 6 tensions here. We already said that's because I'm pulling against my anchor. If I'm pulling with my anchor, then I have 1 less than what my mechanical advantage is. So if we look at a simple 5-to-1, because I'm pulling towards my anchor, right? I've got 5 tensions down here. I have 4 tensions down here because you are holding the other tension in your hand. That's what makes up your 5-to-1. So we're always 1 off, right? So if I'm pulling against my anchor, then I've got 1 more tension up here than I do in my mechanical advantage, what I have in my load. If I'm pulling with my anchor, I've got 1 less tension on my anchor than I do at my load because I'm holding that other one in my hand and not magnifying the force with the change of direction. Where people sometimes get confused is when you get into some of the Spanish Burton variants. So everything makes sense here, right? It's a 3-to-1. Because I'm pulling against my anchor, I've got 1 more up here, so it's 4. But then we look over on this craziness of the 6-to-1 on your Spanish Burton. So what you have to realize on this one is if I'm looking at the 6-to-1 Spanish Burton compared to the 7-to-1 Spanish Burton, right? The only difference is this portion that is a separate anchor, which could be on your harness. It could be on another separate anchor, a progressive, or basically you can set that up on a cam or anything like that. If you get some really weird environmental pathology you're dealing with, trying to get somebody up a mountain and you're just trying to put whatever MA in there to get them across a crux. This is a separate anchor. So when you look at it, the only real difference between the 6-to-1 and the 7-to-1 is this piece right here. This is a separate anchor, where on your 7-to-1, this piece is tied directly into here. So understand that although I've got a 6-to-1 here and an 8-to-1 here, and you're like, that makes no sense. How can that happen? It's because the force that's seen on this anchor is distributed already into this load. If you see it, like 1 goes in, 1 comes out. So this 1 is down here, but it's magnified and put into this number here. So in the end, it's basically the same forces, just with a separate anchor that you see on the 7-to-1 to 8-to-1. So it just so happens that this changes, and this is down here, and this is being pulled on by a separate system, but the force that it generates is magnified into this portion. So that being said, that was a lot of talking. Go back through any of those examples, email with us with any questions whatsoever. The next one, which I would highly recommend, is going to be estimating system efficiency. Counting tensions is one of those things that can help you in certain aspects when you're looking at anchor, or you're looking at, I don't even know what the hell I just built or what the hell you just built, but we can count through and see what we got. Understand that when you're looking at pulley systems, especially when you get into complex systems and Spanish burdens and stuff like that, regardless of simple, compound, complex, basically when you're looking at it with only 4 pulleys, there's over 100 different mechanical advantages that you can create. So it's an exponent. It's psychotic, the amount that you can make with just 4 pulleys and how you place them and what you do with them. Whether you're doing something even, you're doing something odd, you're doing complex systems like a Spanish burden. So with only 4, there's 100 different variants. So that will help with some of the confusion that can arise when you're looking at various systems, regardless of your discipline, whether you're looking at cave rescue, traditional rescue, like technical rescue, canyon rescue, mountain rescue, climbing, and just creating mechanical advantage to get somebody past a crux, not necessarily doing a rescue. The big part is understanding your system efficiency and understanding that I can have 3 pulleys, and all 3 pulleys could be a different efficiency. One could be a bushing pulley, which is like 72% efficient. One could be a sealed bearing pulley, which is like 90 to 93% efficient. And then I can have, whatever I have as my progressive capture in there. And regardless, whether I have a built-in internal cam or I'm having to pull that through a prusik, which is decreasing my efficiency, because I have to go through a device or a rope grab that's meant to cause friction. I'm decreasing that efficiency in my system. This is what will help you understand where each pulley will maximize and increase the efficiency of your system. So where does that lower efficient pulley need to go compared to the higher efficient pulley, compared to maybe I don't have enough pulleys and I just need to go around a carabiner because that's all I have on me. Where do those go in the system? Because that same kit put into a system can go in multiple different ways, and all of them leading to a different system efficiency. So it's the difference between having 3 or 4 people haul on a line and one person being able to haul on the line just by where you place your pulleys and doing it effectively. And then part 3 is going to be a little bit of voodoo with piggybacks, because people look at set of 4s and their piggyback system is just this very basic system. You can actually do a whole bunch with them just by manipulating physics a little bit and exploiting efficiencies, to where we can easily go from a 4-to-1 and with adding 2 more pieces of kit, go up to a 23-to-1 and still maintain enough efficiency to get that haul lift done, especially if you're doing something that's not human in nature, and vehicle recovery or something in confined space, lifting something very, very heavy for a short distance. So that's the next sets. If you have any questions, hit us up at info@elementrescue.com. Thanks.
No, here they come. That Element Clan road rescue shogun, dropping 200 per mantle. Yeah, like what? And rocking killer beats to the eardrum. Click your beaters, tip your hats. I got ice, water flowing up both my calves. Sand flowing down as I hit the crevasse. Don't bother me, man, I got another pass. Element Clan.